Welcome to our IME 143, 144, or 145 virtual screwdriver lab. Today, I'm going to take you through the steps to go ahead and make the screwdriver's body like you see right here on the engineering drawing. So remember, the first thing you do when you go to manufacture a part is you study the engineering drawing. Looking at this drawing, we see that it's a hex part here. You're going to see right here we have 1 inch, and it's a reference dimension because it's in parentheses. That 1 inch is referring to the length of the stock right here. So we're going to actually start off with 1 inch hex stock like you see right here. And one of the things a manufacturing engineer would do is they'd look at an engineering drawing like you see right here. They would determine the raw material size, like 1 inch hex. Then they would go ahead and look at the overall length of the part, 4.00, and determine what length of cut they need to cut their stock on the saw at. So with this piece, we decided to go ahead and cut it at 4.1 so students could get a little practice facing right here. So that's one skill set a manufacturing engineer has, is be able to look at a drawing, figure out what stock size the part needs to start off with. After that, they have to go ahead and figure out how they're going to machine the part. And how you do that is actually something called the manufacturing routing. You're going to see this is our screwdriver routing that we have for this project. And a routing is a recipe for a part. So literally the routing is the part recipe from start to finish. So from raw stock to finished part. Now, as we go through this routing, we're going to follow each one of these steps in order to go from a saw cut part at the beginning, where we cut it on the saw, to a finished part at the end, where we go ahead and wash it, assemble it, and basically we're ready to ship it to our customer. So we have 150 operation numbers, but they go by 10. So there's really 15 steps in order to go from start to finish on this screwdriver part. And again, that's something a manufacturing engineer will do. They'll look at the engineering drawing and they'll figure out, do I need to face the part first? Do I need to turn the diameter next? Do I turn the taper? Do I engrave mechanical engineering on the part? What do I do? What do I do next? And the order of operations must make sense, because you don't want to go ahead and plan yourself into a bottle or into basically a roadblock where you can't hold on to the part anymore. And really, experience and time is what it takes in order to learn how to make good routing without actually stepping into the machine shop first. Now, looking at the routing, our first step was to cut the 1 inch hex stock to length. But because we only have one saw and 12 of you in the lab at a time, we cut everybody's blank to length for you already. So it should be cut at 4.1. Now, the saw leaves burrs all over here. So you'll see this was cut on a bandsaw, not a circular saw. And the burrs need to get removed with a file. So let me grab a file real quick. So, oops, it was on my machine. I forgot about that. But files work in one direction. So you file away from yourself, and you just file the burrs off the edge of the part right here. Therefore, we won't mislocate the part in the work holding. If I don't file the burrs off here, it could mislocate it, and I might be now holding my part on a burr and be out of tolerance. So I'm going to go ahead, file the edges real quick, just to make sure when I put it in the chuck, I don't mislocate it. Now, put that back since it's there. Now, at this point, I have smooth stock, and I want to go ahead and I'm going to face one side to qualify a datum surface. When I look at my routing, I'm going to face the saw cut side number 1 to 4.025 plus or minus 10 thou. So to do that, I need to go ahead and put my workpiece in the lathe. So I'm going to put that in the 3-jaw chuck. I'm going to leave a little bit of material out here, or a little bit of space in the back of the jaw, so I can fit my caliper in there and measure it as I face off. Now, if you remember, the chuck key is what actually tightens the 3-jaw chuck. So we'll tighten that 3-jaw chuck, 2 hands, put the chuck key back in the rack, and I'm going to grab my caliper at this point to just take an initial measurement of my stock. So this caliper, the first step you do when you go to measure with the caliper is you close the jaws, or you wipe off the jaws, close the jaws, and if it's not zeroed out, you're going to zero out your caliper before measuring. Now, when I go ahead and I start measuring the overall length of my part, I get a 4.0900. So I got to take off 90 thou to get it in tolerance, but I'm really, or to get it to 4.0, but I'm really going to 4.025. So my 90 thou minus 0.025 is 65 thou. Now I can't take that all off at once, so I'm going to go ahead and do 2 passes with my turning and facing tool here, this carbide insert tool. So I'm going to go ahead, drop the tool into the tool post here, use my Allen wrench to go ahead and tighten the left-handed nut. Remember, this one is counterclockwise to tighten. So I tighten that nut. I go ahead and I put down the Allen wrench, and I will wear my face shield when I'm cutting, so I will wear my safety equipment. But right now with the COVID masks that we have to wear, they fog up the safety glasses, so we have their ANSI approved face shields when we go to cut. What I gotta first do though is I gotta zero out the tool on the front face of the part, because I want to remove 65 thou from this front face of the part. So to do that, I use the hand wheels to come touch the tool off the front of the part very lightly, like you see right there. Next, I've got to grab this stop block like you see right here, and I snap it onto the ways of the lathe. I then can slide the stop block so it touches the dial indicator right here, and I turn the dial indicator to zero out the indicator so it's 0 on this indicator when it's touching the front face of the part like you see right here. So now, as long as I don't touch this dial indicator, 0 is the front face of my part. So if I back off, out, and go back to 0, I wouldn't be cutting anything right here. And you can actually see the backlash on these LeBlanc lathes. Does everybody see? My indicator's not moving here, but literally my hand wheel moves a good 5 degrees or so, and without even moving that. That's my backlash you got to worry about on these lead screw driven machine tools. When you have ball screws like on those hot CNC machines we have in lab, they have 0 clearance in that ball screw, so you don't have to worry about backlash issues like you do on these manual LeBlanc lathes. So we talked about it. I got to take 65 thou off, or face 65 thou off this part. So I'm going to do my first pass at 40 thou. So what I do is I dial 40 thou into my dial indicator right here. And I have to set up the machine to go ahead and face. So come around to the front over here, and we're going to look at some of these settings on the machine. So in order to face, we have the 2 different directions for auto feed right here. We have forward and reverse. For facing, we go this direction and we back out. So we want to be in reverse gear. So you'll see the blue down here points to reverse. So we're in reverse. We're going to stay in fine feed rate because we're going to stay in the smaller chip loads down here in the chart. And I like to run a 6.5 thou feed rate with these carbide tools. So I move this lever over to that 0.0065 slot. I'm in fine, but in order to make sure I'm running 0.0065, I got to be in B. Right down here, we've got C, B, and then A all the way over. So I got to go ahead and lock it into B like you see right there. Now, I'm going to move my shield down for a second, and when I turn on the lathe, you're going to see there's this lead screw down here. What that lead screw does is it keeps the carriage timed with the actual spindle right here. So this is a fully mechanically geared machine. So that lead screw connects here. When I pull up on my feed lever right here, it's going to connect to this lead screw and give me a constant chip load of 0.0065 inches per revolution as I feed across my part, or I feed this way and then back out. Now, let's do that. So now that I've got my depth of cut set and my lathe all set up, I'm going to drop my safety shield, go ahead and turn on the lathe, and I messed that up. Give me one more second. Come right over here to 40 again, get close, and then basically I am going to cross feed by going out and down. When I get slightly past center, I stop auto feed and I pull up to back out this way automatically. And then I turn off my lathe. So auto feed allowed me to go that direction and then back out that way using reverse. So I got to get down to 4.025. I know I didn't do that on that one pass because I didn't take off enough, but I'm going to measure before I go ahead and take my next pass. So when I measure here, we're now at 4.048. So I got to take off about 23 thou right there. So I can do that. I can go ahead and I want to just come touch again to see where I'm at. You can see I'm at 40. I'm at basically at 40 there, but I'm going to re-zero it. I'm going to back out, off, and now I'm going to go to 23 thou right there. So at this point, I'm going to put my safety shield back on. We're going to go ahead, turn on the lathe, get close, and we go out and down throttle speed. Speed across our part, so we're facing the part, changing the length. When I get to the center, I go ahead and stop and then pull up to back off automatically, and then turn off the lathe. So that's going to be, hopefully, our first step. Let's go ahead and measure the part. So I've got, just so you can see, 4.027. So I'm 2 thou out from the exact measurement right there. So we're within tolerance. That means it's time to go on to the next operation step. Now, what quantifies an operation step is work holding. Whenever I take a part out of the work holding, I've lost its position on the machine, so I'm now on to another operation. So I'm going to take it out of this work holding. We now lost the position in reference to the dial indicator down here, and I have to go ahead and look at my next step of my routing. I have one machine surface now that got faced, then I still have my saw cut surface back here. The machine surface is actually going to end up being the front of the part, or the front of the screwdriver. So we're going to now go on to the next the next operation, which is operation 40. In operation 40, we're going to go to a Haas CNC machine, the mini mill, and we're basically going to put it in a collet chuck. So join me over there, over here on the Haas machine. So this machine just got powered up and restarted, and what we're going to do is we are going to install the thread milling tool as tool number 1. So we never leave a tool in the spindle, they get stuck. So I'm going to put this tool holder in the machine right here. So you're going to see this is actually a 60-degree tool that's going to go ahead and do some helical thread milling on the outside of our screwdriver. So I'm going to put this in. Now that that tool's installed, we're actually going to end up using a collet chuck to hold onto our workpiece this time. So collets can be used in mills and lathes. You're going to see we have that collet chuck right there. And to ensure that our part doesn't sit up too high, once we put it into this fixture, we've made this gauge. This is the height gauge right here. So the first step would be to close the doors, blow out your collet chuck. Make sure you're not going to locate on any chips down in there. And we're going to then put the 1-inch stock into the collet. Now you have to go ahead and clamp this down. So we're going to clamp it down. What it does, if you see the collet's being drawn down into the collet holder, or this is pushing up, it doesn't actually change height. And that concentrically collapses around the workpiece and now holds this workpiece for milling. Now before I let go of this, I just want to make sure that my gauge fits. So you'll see this is a thing that you can do. You can gauge products really quickly to see if they fit or not. So if this wasn't sitting flat and there wasn't a little gap under here, the part wouldn't be sitting in there correctly, and we wouldn't want to press the green cycle start button, or you might crash the machine, and that's a bad thing, is crashing machines. So that's our height gauge right there. Now that we've tightened this, I'm going to go ahead and close the doors. I'm going to come up here and double check that I have the correct operation program loaded. So you're going to see it's 145 SD body, op 40. So this is going to be op 40. We're going to thread mill the top of the screwdriver. So the order of operations is going to be, it's going to face mill, it's going to contour mill around the top of the part in order to make the profile, and then it's going to do a thread relief with a T-slot cutter, which doesn't always need to be done with thread milling, but in this case it looks good. So we do a thread relief, and then we're going to come and do a helical path around with that thread mill and cut the threads into the actual part. So here we go. We're going to go ahead, press cycle start. Once we're in memory mode, the machine is going to go ahead and grab the 2-inch face mill. So we're facing the final length of 4.0 on the part. We're now going to grab our 3/8 end mill, and we're going to contour around the outside edges of the part. So I just wanted to show you there, at this point, we've contoured the major diameter of the thread and we face it to the correct height. So we're going to use that T-slot cutter that you see right above there to cut that thread relief in the bottom of the part now. So that's known as a T-slot cutter. Back out. We'll go back to forward, coolant, and we're going to make a relief under there, an undercut. We'll show you what it looks like in 1 second when it's all done. So we're slowly going around the part, doing a nice relief cut. And remember, our feeds and speeds are set up a lot slower than they would be in industry just because we're a freshman beginner lab here at Cal Poly. One more finish pass here. So what that T-slot cutter did is it cut an undercut or a relief from the part. That's what's nice about T-slot cutters. You can kind of see that slot around the part. That's where the threading tool is going to stop for our thread relief. At this point, we're bringing in our 5/8 90-degree spot drill to go ahead and spot a hole. Normally, we would pick spot drills with a larger tip diameter than our drill bit, like a 120-degree spot drill, but we're out of tools in this machine, so we use our spot drill to go ahead and spot and go ahead and chamfer the part. So it's going to basically chamfer the top of the part as well with this spot drill. So we're going to go ahead and turn the spindle back on, cool it, and then here we go. Well, I forgot. I guess I don't spot it. We're going to go ahead and thread mill it here now. So what the thread mill does is it creates a helical pattern around the part. So it's moving down at a helix the same pitch that our thread will be at. And it's going to do it in multiple passes. So that was the first pass. Now it's going to come basically bring itself in a little bit on the step over and do the same pass over, just a little bit tighter. Same pitch of the helix though. This is the last pass, and then we're going to drill a hole for the magnet. So before we go on, I just want to show you what the helical thread milling did. We created a thread on the top of our part like you see right there. We created 7/8 14 thread there with that helical thread mill. Now we're going to drill the hole for the magnet. So we peck drill on parts to go ahead and clear chips. So we slowly peck at 1/8 increments. Actually this peck is at Q.125, so if we look up here with the code, it's telling it to go down to 3.5 inches overall and give it a peck increment of 0.125 at 18 inches per minute. So there's our feed rate for the drill, and then there's our peck increment. It's XY 0 right in the center of the part, and then 3.5 inches down. So that was right at the limit of what that drill could drill. It's like at the end of the flute length right there. Now if you're a programmer, it's always nice to put the original tool back in so it's ready to go again and bring the table forward for the operator. So I'm going to go ahead and blow off the part. A nice little trick is put your hand around the door like this. That way you don't get blasted in the face, so we don't get Brian into gimbal. So when I loosen this now, I'm going to take my part out. I've got my face side here. I've got operation 40 where I just helical thread milled it. I cut the relief with the T-slot, and then I drilled the hole for the magnet to go ahead and drop down in when we go to assemble the screwdriver. Now because I don't know where I'm going next, I'm always going to refer to my routing, right? That's the engineering documentation, tells you how to get the part done. So if I look at this, I'm now going to go on to operation number 50. I'm going to drill the hole for the roll pin. So let's move on over. I don't know where to go, so I look at my routing. I'm going to Haas CNC Mini Mill number 1. So 3, 2, 1, here we go. Now with this one, all these machines were just powered up, so we're going to jog this over. I'm going to go ahead, put my part down for a second. I'm going to grab tool number 1, which is our drill. I'm going to go ahead and put that in the spindle. Again, we don't leave our tools in the spindle overnight. And now I've got to go ahead and read my routing real quick because I want to see which way I got to go ahead and put it in the vise right here. So to put it in the vise, I'm going to go ahead and put it this way for this program. So I put it in here, put it down there. I got to go ahead and move around the cameraman. And I'm going to grab my torque wrench now and tighten my vise. So I'm going to go ahead, tighten down until I feel it break away. See that? That's how the torque wrench works. Probably gave it a little bit more than I should have. Showing you how the torque wrench works. I always just pull on my part a little bit to make sure we're good. So pull on it, make sure it's nice and clamped. At this point, we're ready to go ahead and drill the roll pin hole. So I'm going to close the door. I'm going to double check. My program says 145 SD body op 50. So we're now on operation number 50, drill roll pin hole in screwdriver body. So I'm going to use a 3/16 jobber drill and basically drill a hole so we can press a roll pin into it later. So I'm going to hit memory, reset, cycle start, and here we go. We're going to go drill. Well, that was easy. That's all done. So I'm going to open the door, blow it out. Then go ahead and switch my wrench so it's loosening. Loosen it, and basically pull my part out. So what I did there is I drilled that cross hole for the roll pin. Kind of see that right there. Now, see it right there. So now, I don't know what to do, so I look at my routing. My operation number 60 says drill magnet hole and drill bit storage cavity hole. It's actually, that's a mistake. It's just drill bit storage cavity hole, because we already drilled the magnet hole on there. So I have a typo on my routing. But what we're going to need is a 9/16 Morse taper drill with stop, a chamfer tool, and our chuck. So I happen to grab this 9/16 drill with a stop. Now, if drilled holes aren't a tight tolerance, you could go ahead and put a stop and come right up to the edge of the stop without rubbing the stop on your part. So this is a quick way to judge the depth that I have to drill this 9/16 hole in the lathe. So join me on the lathe to do that. So what we're going to do is the tailstock, put my part down, the tailstock has what we call a Morse taper in here. The Morse taper, they come in different sizes, but the taper provides basically the torque, or the resisting torque, to keep the drill bit from spinning as it's going ahead and drill. So the taper not only self-centers, it kind of provides the gripping force on the tool to keep it from spinning. So what I'm going to do is I put the taper in, and I like to give it a nice little snug push in, because now I know that it's not going to come out. And to do this, I no longer need this turning tool right now. We'll bring that back out when we turn the taper later. So I'm going to loosen this. I'm going to go ahead and basically take this and move it away, because I don't need the carriage for right now. So I'm going to move this forward. If you can't move your tailstock, there's a hex wrench that you see right here that I can go ahead and loosen and tighten it. And I'm going to put my workpiece in the 3-jaw chuck, and I'm going to clamp down on it right here with my chuck key. So once the chuck key's good, I put it back in the rack, and I bring my drill bit forward. At this point, I'm going to use my wrench, my 7/8 wrench right here, to go ahead and tighten the tailstock down so it can't back out this way. It's the most common thing students do, is forget to tighten the tailstock, and they think they're getting really deep, but it's the tailstock going backwards. So I'm going to drop my hood now. We're going to go ahead and turn on the lathe. And I'm now going to pet drill at it. A little oil goes a long way, so I'm going to add a tad bit of cutting fluid up there. And we're going to start petting. So you do nice little pet drills at it. So what I'm doing with the hand wheels, I'm going forward a little bit and then back a little bit. That allows the chips to go ahead and get relieved. If I just drive it through, it'll do it. It's just it's going to heat up and destroy our tooling a lot quicker. Sometimes when it starts stinging like this, I like to back my drill out and just get rid of some of those extra chips in there. remember, this isn't a critical measurement, so we're just going to get very close to that stop. All right. We back it out. We turn off the lathe. We go ahead and we bring this back. And in order, this is now stuck in here, right? The Morse taper. But to get the Morse taper out, we just back the tailstock all the way out and it pushes against this back edge and pops it out of the machine right there. So literally, we just drilled our 9/16 hole. I'm going to look at the routing to make sure I didn't miss any steps along the way. So I've got to go ahead and drill the 5.563 diameter hole. We just did that. Now we need to chamfer the hex vertices and storage hole. So to do that, I need to get a chamfer tool out. I'm going to go ahead, find my chamfer tool up here. The chamfer tool is the 45-degree angle tool. It's a neutral tool that goes both ways. Kind of see that? So I could cut a chamfer on this side or that side. That's making it a neutral tool. I can cut this way or that way. As compared to this turning tool that you see right here is a right-handed tool. When I hold it in my right hand, that's the only way it can cut, the way I swipe like this. So the cutting edge is only on that side. Where the neutral tool, I can cut both ways technically with it. So I'm going to put the chamfer tool on the tool holder here. We are going to tighten it down. We are then going to come up over here and flip down our shield, come in. I'm barely going to touch the inside edge there. I'm good with that. Now I'm going to come back out over here, and I basically just broke the edge on that one right there because it's a chamfer. It just got to look good. But on out here, we have a value. I have to look up the value for my chamfer on my engineering drawing. And when I see it, I see basically I've got 6 by 20 thou by 45 degrees. So honestly, I just need to make a 20 thou chamfer right there on the part. I'm going to do that. I'm going to basically come up, touch it. When I hear it touch, I'm going to look at the number and add 40 to it. Because it's 40 on diameter, 20 thou in radius. Remember, the cross slide reads in diameter. So I'm literally, flip my shield back down, turn on the lathe, move over, and when I hear it make a noise, right there, it made a noise. I'm going to look down at my number on my cross slide, and I'm going to add 40 to it. Now that's a really small edge break, right? That looks just like it on the drawing. But I'm going to go ahead and make it out of tolerance because I want it to look a little bit better than that. So that's, usually chamfers are cosmetic. So again, if it's not 20 thou, if we cut a little bit more, it's not going to be a big deal. So I'm going to flip that back down, turn on the lathe, and eyeball this one. So at that point, I just made a lot larger of a chamfer. That was my choice, though, is my part. So there you can kind of see I chamfered the hex right there. So now we're going to go ahead. We're going to take this tool out, and I don't know what to do next. Where do I reference? My part routing. So I come over here, I look at operation number 60, was basically drill the drill bit storage cavity hole, chamfer the part. Now I'm done with this side of it actually. I'm going to go ahead and go on to operation number 70, which requires a surface plate, a Sharpie marker, a vernier height gauge, and a carbide scribe. So I'm going to go ahead and scribe the location to turn up to. Looking at the drawing right here, we go 1 inch back from that edge right there, or 3 inches back from the datum, right? So I can go either way here, but I'm going to go ahead and go from where it's measured right here. So it's 1 inch back, and it's 18 degrees. We got to turn this lathe to, or turn this taper to. So I'm going to mark the vertices where I'm going to stop turning at for my part. So to do that, we'll go ahead and pull this out. And we're going to move over to the surface plate. Now, our granite surface plate, let me get a little alcohol and clean this thing. It's a little dirty as is, just looking at it. We're gonna clean it like this today. This is definitely not a calibrated surface plate, but it's good enough for us. There we go. Just wanted to clean it up a bit. But what we've got here is we've got our height gauges. Remember, these height gauges have a carbide scribe. So this is our datum surface, our granite surface plate. So when this height gauge is at 0, it's touching the bottom of the surface plate. So all the heights are related off of this datum. So what I've got to do is I got to bring this to 1 inch. I get it close and I lock down the top piece. And I actually can't see, so I have to pick it up. And now that I lock down this top one, there's this upper adjustment right here that allows me to do the fine adjustment. So I move this wheel till it's exactly 1, and then tighten down the second adjustment there. At this point, I'm going to go ahead and use my Sharpie marker to only mark the vertices. So I'm going to mark only on the vertices so I can go ahead and see where I scribe a line right there. So you just kind of do this. Remember, it comes off with rubbing alcohol, which we have an abundant supply of thanks to COVID now. So move over here. I'm painting just like Bob Ross, if you know who that is. Actually, he's used pastels and watercolors. I got a Sharpie. But what we got here? So now that I've marked it, I'm going to use this height gauge that's set at 1 inch to go around and mark the vertices on my part. Well, that would be nice. This wasn't tight. There we go. So we mark the vertice. We mark the vertice. Mark the vertice there because we're going to go right up to that point. We'll go right there. Go right there. And that was that one more there. There we go. So now I have marked the part where I'm going to turn up to on my taper right here. So that was operation number 670. So moving on, after we're done with operation number 70, we're going to turn the 18-degree tapered end, and basically then we're going to center drill and drill the pilot hole for a tool called the broach. So I'm going to put my workpiece in the chuck. You see right here. I'm going to go ahead and close down my 3-jaw chuck, use both hands. Now, this is where the setup gets confusing for some students. We've got to go ahead and turn a taper. If you remember, the taper is made with the compound slide, right? So we have the cross slide and the compound slide. Well, looking at this, I'm going to loosen this tool post first. That's loose. I'm now going to loosen this. I'm finally moving the compound off 30 degrees. And when I go this way, let me loosen it a little bit more. When I go this way, you can see down here there's a protracted angles. Can you see that on this side? But the 0 point's right here. If you look, there's a 0 on the lathe. So the 0's right there that we read off of. So I've got to line that up. When I go right here, it's 90. Well, I want to twist it this way minus 18 degrees. So 90 minus 18 is 72 last time I did the math. So I'm going to set this to 72 degrees right there. So the 72 is lined up on the 0. Now, what I'm going to do there is I'm going to go ahead and I'm going to tighten the compound down. So we tighten that compound down. And I'm now going to put my turning tool in like this and just line up this tool holder so it's square with the compound slide. I don't have to measure anything because the movement of this compound slide is going to cut my 18-degree angle. Last but not least, I tighten my tool down, and now I'm ready to go ahead and start cutting. So to do that, I get close. Get this way. Let me do this a little bit. Do this a little bit. So what I'm going to do is I'm going to cut in this direction to cut a taper on the part. So I put my mask down, I go ahead and I turn on the lathe, and I'm going to move my compound. So you'll see I'm slowly moving my compound slide. So I turn, I back, I do a little bit more depth of cut, do another turning pass,
And I'm going to stop when my turning pass hits my line in the back there. So I got a ways to go. I'm going to take a bigger cut this time. This is bigger than I'd recommend students who are beginners to try it first, but this will work. You can see it's done cutting there, so I back back. And then again, we're really only worried about that final finish pass. We're going to talk about that before we do it in the surface finish call out on there. So moving forward. So I'm going to stop real quick. I'm going to back it back out and just show you some things real quick and talk about surface finish before I finish out the last couple passes.
So, looking at the part, I want to turn up to this scribed line. Can you see that right there? I scribed the line 1 inch, so that's where I want my turning to stop. And that's why I only scribed it on the vertices, because it kind of starts to look like a pencil. You see that? So I'm almost to my finish pass. But before I cover that, let's look at the drawing real quick. The drawing has this, it almost looks like a square root symbol, right? Well, that stands for surface finish on an engineering drawing. So you need to achieve a 62 surface finish, which is a nice machined finish. Anywhere between 62 and 34 or 32, right around there, is a machined finish that you can easily get off a mill and a lathe. So we want to make sure on our finish pass we get a nice constant feed rate on this compound's hand wheel right there. So I want to make sure I'm always feeding the same amount so I don't see any lines in my part. So let me go ahead and do one more pass and then a finish pass. So I turn it on, I drop down the depth of cut. Here I go. This actually might be my last pass. It's looking pretty good. Coming back out a little bit, off for a second, turn it off, and let's look at it. I covered right up to that line. You can see it's right, it's not even there anymore. So I'm going to call that my finish pass. That's easily a 62 surface finish. We are good to go on that one. So now at this point, I'm going to go ahead and put the lathe back to the original 30 degrees on the compound, because I don't want to, I'm going to go ahead and do a chamfer. And it's always good to put things back exactly how you found them in the lab. So to do that, I'm just going to loosen the tool post, put it back this way. Remember, it's the motion of the machine tool. So if this is off a little bit, it's just going to change your lead angles that we talked about in class. So we got that. Go back here, loosen these two, and back to 30. Remember, the reason we picked 30 degrees is because the sine of 30 is 0.5, and we know that this is a 2-to-1 ratio regularly, but this way this leg is 0.5. So this is actually a 4-to-1 ratio on length if you were to go ahead and do the trig on it. And that's why they do that at 30. So you know your ratio is 0.5 for whatever you dial this in. So you would dial 4 times on this one to figure out how far you're going in instead of a 2-to-1 ratio. Probably just confused you. You don't have to remember that. Now, last but not least, I should have aligned that straight like this. And we are good to go. Now, I'm going to grab my chamfer tool this time and do a chamfer on the outside. If you remember, the chamfer was 20 thou, but I'm going to just make it look good. I'm going to get it very close to 20 thou. Close it down, turn it down, move on over. You line up the chamfer tool right in the middle of the tool like you see right there. And I'm going to actually show you the real way to do it. Now that it's touching the part, I move this cross slide dial right here, the friction lock, to 0. See, it slides as a friction lock. So I can friction lock it right there as long as I'm holding onto this handle. Now I'm zeroed. So I back out. I go ahead, I turn on the lathe.
and I dial it into 40. So now we have the chamfer on our part right there. So at this point, I'm basically going to be drilling. So I'm going to take my chamfer tool out. We're going to go through and we're going to grab the center drill. So we're going to use a center drill to center our holes in this lathe. Really, a center is made for a live center, a 60-degree live center, and you would want a spot drill like 120 degrees if you're really worried about locating. But I'm going to move this out of the way. I'm going to bring this, I got to unlock it, bring it forward, lock it down, and I'm going to center drill up about 80% up the cone right there. If I'm good, I'll go ahead and make a little bit of a chamfer for the actual hex afterwards. So we're going to turn on the lathe. We're going to bring this in and we're going to center drill. So when I get most of it in there, you're going to see we have a nice starting spot for a drill bit. What drill bit do we need? I don't actually know, so I'm going to consult my routing. I think it's a 1/4 inch, I'm pretty sure it is. But when I look at my routing, I see that I'm going to basically use a 1/4 inch high-speed steel jobber drill and in a basically Morse taper adapter. So I've got to run over and get that. I left it by my height gauge. So this is a Morse taper drill. It's got a Morse taper adapter in it. There's an adapter and an adapter. So it's been adaptered twice to get it to fit in here. And what we're going to be doing is we're drilling a through hole for the new conventional manufacturing process that you learned about in lecture this week called broaching. So when I bring this forward, any type of internal broach needs a through hole in order for you to broach the part. That's a test question. So know that you need a through hole in a part in order to use a broach. So I'm going to drill a 1/4 inch through hole in here for our broach. Now, when I turn the power on, I'm going to come over here and basically peck drill. You see the thing self-center in the hole there. So we're peck drilling. And I made it through. I knew because it just stopped cutting. So we made it through. I'm going to back this out and turn off the lathe. I think we're done with operation number 80 now. That was operation 80. So I'm going to do this. Now I'm going to put the tools back in the rack to make a good example, right? That's really bad that I didn't do that. Now looking at my part, I don't know what to do next, so I'm going to read the routing. And operation number 90 says deburr and chamfer roll pin holes. So let's go to our deburring station over here. So I have these hole deburring tools here. Let me go ahead and disinfect that. IPA it. That's what we do. IPA up everything nowadays. So now, it took off our Sharpie marker too, right? We're all good. So at this point, I would go ahead and deburr. It's a 45-degree tool. It's got one flute in there to go ahead and cut the chips. You put pressure down, and you go roundy round, and it makes a nice little chamfer on your part like you see right there. So again, roundy round, and we got a nice chamfer on our part. So literally, that was operation number 90, deburr and chamfer roll pin holes. Now, there's also a hole inside of here when it drilled through. There's some flash inside there. So I want to take a W-sized drill bit, and I just go back inside and I twist it around to get rid of and be deburring the inside of the hole. Because I drilled this hole before I drilled the cross holes. So when I drilled the cross hole, it left some burrs inside there, and when I go to put my magnet in there, those burrs might keep my magnet from dropping flush into the hole. So that's what you got to do there. So now we deburred our part. So that was operation number 90. Operation 100 is the broach. Let's go ahead and check out our Pioneer broach built in California. So this is our broach. It's a hydraulic powered broach. So the process is broaching. The tool is called the broach. The machine tool is called the broach. The tool is also called the broach. And what we've got, and my grandma wore a brooch to church, so you know, so that was a totally different thing, right? English language. But what we got here is we've got chips, right? We're gonna go ahead and brush off of our chips there. But check this out. The brooch is hex shaped. So it's gonna be able to create sharp internal corners such as a hex on the inside diameter of this part. When I grab the engineering drawing, you're gonna see, in order for it to hold the screwdriver hex bit, 1/4 inch one, I need to make a sharp corner feature inside there. I cannot machine sharp internal corners any other way other than a brooch, hence the process. So to get that 1/4 inch hex, we're gonna broach that feature in there. Now, the brooch works, I made this little fixture to hold your part, and I put the brooch down through the hole I drilled in my part. I have this little detent right here that'll lock it into place. It will in a second. There it goes. It gets sticky sometimes, but now this is, see, it slides 90 degrees. So it's literally a knurled knob that's open, that's closed. Clockwise is closed. This is a hydraulic powered machine, so what it does is it uses the hydraulic oil for its cutting fluid and the power of the machine. Now, I'm going to close my safety shield. I got oil in my hands. I'm going to get a rag for that in a second. But when I go ahead and I turn the power on right around here, I make sure the handle's up, I turn on the power, and then I put the cutting fluid nozzle over the brooch. Give me 1 second. I'm going to flip this switch. And make sure you do not adjust this because it will adjust the oil like crazy. And check this out. I love the harmonics on this one. Listen to it while I pull this lever down. Now that it's down, I turn off the coolant over here, the switch down here, and I pull my part off before I send the brooch back up. And then I got to go ahead and take my brooch out of the holder, and I put it back in right here. What I forgot to do is I forgot to come to the game with a rag. That was my bad. And I'm going to turn off the power. So down here, we've got rags. Brian, our lab tech, luckily supplied us with those. Thank you very much, Brian. So I'm going to wipe my hands off and then wipe off my part on the rag real quick to get all the oil off. We don't want to track oil around there. So this is cutting fluid, this oil. Instead of an emulsion like you see in this Haas CNC machines we have straight cutting oil in the brooch. But what the brooch did is it cut this 1/4 inch hex in our part. So you'll see I now have that 1/4 inch hex with sharp internal corners that I can put a screwdriver bit into. Perfect. So that operation's done, and because I set my center drill in there deep enough, it made a chamfer. It's a 30-degree chamfer, but who's gonna know? Nobody. So, unless you inspect it. Now, when I move back over here to my mess, let me just move this out of the way. I don't know where I'm going next, so I have to actually read my routing. So, my next step is to clean and wash my part with simple green solution and water. So I'm going to go clean it out in the sink real quick before I engrave CNC engraving the mechanical engineering logo. We'll have everybody's major available to go ahead and engrave on their screwdrivers, but this isn't originally a project I made up for the mechanical engineering class, IME 145. That's why it says mechanical engineering on the logo, but we can engrave everybody's logos on them. So let's move over this way. We are going to open up this machine, and I'm going to wash it in the sink real quick with my cleaner. 1 second to do that. I'm actually going to use IPA. The buckets should be cleaned out. There's a little bit of dirty water from the last class a few minutes ago in the bucket, or else I would have put it in that bucket, but I don't know. Do you want to put your hands in there? Probably not today, so we'll clean that out. It's Friday. It's almost 5 o'clock. That's the reason why they're dirty today. So, what I didn't want to do is mix my cutting fluids. I didn't want to mix the brooch oil with my emulsion over here in my CNC machine, so I went ahead and tried to clean it as good as possible. Of course, there's going to be a little bit that mixes, but as long as it's only a little bit, we should be great. So, on this one, we're going to go ahead and I'm going to show you something on the control, and I'm going to talk about that real quick, then I'm going to switch to the mechanical engineering program. This traditional one right here is called a macro CNC program. If you look, the macros CNC program is completely different than G-code. What it does is it asks for user input and allows you to engrave multiple things. So when I press cycle start, what it does is it pulls up a PDF of what I can choose for my engravings. So I could press 1 for this logo, 2 for that logo, 3, 4, 5, and 6, and get different logos. So I could have the manufacturing engineering logo, which why would anybody want anything other than manufacturing engineering? It's the best major ever, right? But if you did want another major's logo, you can select 2, 3, 4, 5, or 6. For right now, this one's a special limited edition fall 2020 COVID engraving. We're going to get basically a new set. We're no longer doing the fall 2020 edition, so we don't have to write a program every quarter, a new set of macro programs. So I'm actually going to hit reset, because I'm going to reset that whole thing. I'm going to go to my list programs, and I'm going to basically grab screwdriver body from last year, the actual logo, the IME logo that goes on the part right here. So to do that, I'm going to make sure that I have the screwdriver body op 120 program. It's got all my information right here. And now I'm going to go ahead and put the part in the machine. So to do that, we have to open our door. We're going to put the part in. Butt it up. I was just noticing the jaw's a little deformed. I like to blame that on Zimmerman at all times. Oh yeah. So, give me one more second here. There it goes. So, give me one more second. We're almost there. I'm going to put it right on that surface. There it goes. So students tend to try to basically bring these vices to the extreme limits of travel, which you don't need to do. It's literally you do a quarter turn and then loosen it in the back. We're going to shoot a video on how all that works. I'm basically seating it down with my dead blow hammer, and then I torque it down right there. Now I'm going to go ahead and close the doors, press memory, reset, and then cycle start. Here we go. Now, what it's doing right here first is it's going to make a level surface to engrave on. So basically, I just cut a surface to engrave only 2 thou deep. If you don't do that, it'll be the engraving that only goes down 2 thou will not be uniform. And I'm going to turn off the coolant so you can kind of see this engrave. I'm going to splash it. But you can see it's using a 16th inch ball end mill to engrave mechanical engineering on it. So we'll pause real quick. We're going to go through all this code. So it is verifying that it's hit every single one of those XY values before it goes on to the next line of code. This thing can think quicker than we can even react. So as you see, it's just cruising down. It's just XYZ values to write mechanical engineering and Cal Poly and put the little gear in there for the ME logo. Almost there. So when we're all done, we switch back to the original tool. And then we send the table forward for the operator. Remember, ergonomics is part of engineering. So I'm going to blow the part off. I'm going to go ahead and I'm going to unclamp the vise. So remember, to open the vise, it's literally, you just loosen it like that, and after that, you just push down a little bit like that, and you're done. It's really pretty straightforward. But looking at the part, we engraved mechanical engineering and Cal Poly on it. Kind of see that? Perfect. Now, I don't know what to do next, so I'm going to go back and look at my routing real quick. So moving right here, I got a routing right here. They're all over the lab. You're going to see we just engraved mechanical engineering logo. Now all I got to do is brush in the hex surfaces and wash with water. And first article inspection, I'm going to skip that for next week, and I'm going to actually show you assembly this week. And then we'll end up doing first article inspection next week on another blank screwdriver that I have. So real quick, what we're going to do next is we move over here to the Scotch Brite Pad. And because this was used by somebody else, I'm going to IPA it real quick. Forgot to IPA my own Scotch Brite Pad at the beginning of the day. So since I'm dripping, I'm going to stay over the trash can. This is an abrasive pad. It's called Scotch Brite Pad. They make green, they make red, but red is actually how we get that brush surface. So in 145, we talked about this, right? We talked about fixed abrasive texturing. And we talked about brushing, and like if you go to Chipotle, you see the brush surfaces in the back by the kitchen there. And all we're doing is basically brushing those extruded surfaces to get this brushed aluminum look. You don't want to brush your machine surfaces, but watch, I can get rid of that mark on my part, the ASM mark. I can go ahead, brush that surface. I'm not going to spend the full time on camera doing it because it takes a little bit of time, but let me just do major parts of it so I can show you what that looks like. I don't want to brush my machine surface either. I'm just brushing the extruded finish of the part, the extrusion that we didn't ever machine. So there we go. Whoops. Now I'll go ahead, spray off the part a little bit more, get myself a COVID wipe. Super, super wet, but you can see, let me dry it off now. But you can see that brushed aluminum finish. Does everybody see the difference between a machined aluminum and a brushed aluminum finish? So that was the purpose of the Scotch Brite Pad, to give you a nice little satin finish on the part and take off any of the extrusion marks that were on there. So we have basically finished a part from start to finish, if you think about it. So we have made this entire part. We don't know if it's to print yet. We don't know if all the tolerances are correct, but we should be inspecting it as we make it through the different features so we don't put a lot of value, wasted time into it. We're going to talk about that next week in our 4th virtual lab, where we go through and we're going to make the cap, the threaded cap for the top. We're going to learn about knurling. We're going to do some helical thread milling in there. And then we're going to basically do a little bit of a cost analysis on this part to figure out how much this would actually cost us if we were to go into business and making these parts, and where all the different costs in manufacturing come into play. But I want to go ahead and just finish this one out and assemble it to show you how this screwdriver works, minus the cap, the threaded cap. So I'm going to grab my screwdriver assembly parts over here in my Vidmar. Over here in my Vidmar. That's soft job. Project hardware, tooling, hardware. There we go. Project hardware. They're nicely labeled. So I'm going to grab a flathead. I'm going to grab a Phillips. I'm going to grab a slotted roll pin, and then a magnet. Magnets are always hard to get apart. I got this. There we go. There's 2 magnets together, and they're so small they're hard to get apart. But join me on the arbor press over here, and we're going to go ahead and put this thing together. There's this small magnet that you see right here, a little 3/8 inch diameter magnet. This is really cool. Actually, you can see the eddy currents taking effect. So if you can actually watch it drop down into the hole right here, you're going to watch it drop really slowly. You ready? Did you get to see that? Or let me do that one more time. It's really cool watching the eddy currents. Ready? Did you see it slowly? I think that's really cool. I don't know. Whoa, there it goes again. But I can do that all day. So at this point, we made this little assembly fixture here for it. I like to use my screwdriver bit instead because it's a little bit longer. But what I got to do is I got to grab the magnet and make sure it doesn't. You're going to see right here in the roll pin we want to make sure that the magnet stays on this side of the roll pin when we press it. So we actually have this assembly fixture to do that, where it slides in and it keeps it from going this direction and covering up the hole when I press my pin in. So that's all this is made for, is to assemble. Now I'm going to put this on the arbor press like you see right here. This is where you got to be careful. We have this other fixture. It doesn't fit it anymore, I don't think, though. Let's see here. Nope, it doesn't fit it. So we used to have a fixture for that, but for now we're going to go ahead and line it up by hand. Line our roll pin in, and we just get it started in the hole. So this is known as a slotted roll pin, and it's like a spring roll pin. So we drilled a 3/16 hole. This basically flexes this roll pin and captures itself in the hole. So that's like how some types of shift linkages are attached to transmissions sometimes. But when we have this ready to go, we go ahead and just press it down in. This is a press fit. It's going to be in there permanently until we press it right back out. So I pressed my roll pin. The magnet made it stick a little bit, right? And that roll pin now sits flush in the part. And I just pulled out my thing here, my assembly tool. Now what this will do is I have basically the magnet in there, and it now magnetizes the screwdriver bit, and now I have a hex screwdriver where I can have all my bits. So I can have this bit, or I can have a Phillips bit, and so forth. And they have room in the back to go ahead and hold on to them. And then we're going to make a cap next week for them, and you made an American-made tool. So we made in the USA screwdriver, right? So you can see all the part. You could get more 1/4-inch hex bits for it, Allen drives, and so forth. But they all just sit there in the back and stored, and they're right there. Funny story about these screwdrivers. I found one out in the desert, a place called Rock Front, which is way out in Santa Maria. I was riding my dirt bike, and I saw this thing on the trail. I was like, that looked like a screwdriver for my class. There's no way. This was back in 2017. I turned back around, and sure enough, it was a screwdriver from 143 out in the middle of the desert. And I actually found the student. His student's name is Nathan Harry. I believe he works at Haas now. I'm not sure where he's actually working. But that student, basically, he was really excited. And basically, I gave him back his screwdriver. He had it on his dirt bike and happened to lose it on his dirt bike. And I just found it out in the middle of the desert, 2 miles in. It was pretty crazy. So, I mean, these things go all over the world, right? Think about it. But hopefully you've enjoyed the process of us machining this screwdriver body out of 1-inch hex stock right here. It's a great project. So join me next week for our virtual lab number 4, where we're going to make the knurled cap that gets helical thread milled on here, and it has a hole to go ahead and put it on your keychain as well. So have a great week, and I look forward to teaching you about the cap on week 4.